Once again, a very warm welcome to one and all present over there. I, Varnika, I am going to introduce myself first, that I am Varnika Mehta and we are just going to study about the mass defect and the binding energy. Alright? So we have earlier covered few topics related to the structure of atom, and that topic was the nuclear energy. In the previous session, we have covered about the nuclear energy. Alright? So what is that nuclear energy? I'm sorry, that was nuclear force that we were talking about. So what was the nuclear force? If we are going to just take a revision of what nuclear force is, so let me just write the definition once again before you. And so the nuclear it is that strongest it is a strong attractive force between nucleons in the nucleus of an atom. That was called as nuclear force. So basically we have covered this topic in the previous session, and that was nuclear force. And we have learnt so many properties of the nuclear force, that it is an attractive force, it is the strongest force in the world or in the universe you can say, and it is a non-central force, and so many things about this. Now the topic of the session would be, first of all, we will be discussing about the mass defect, and then we will move to the binding energy. Now you are just knowing that. Okay, so let me come here so that you can note it down. So you would have seen that a nucleus is a compact material you can say, in which protons and neutrons are present. Alright? Now we have seen that since proton is present inside, there are a number of protons inside the nucleus, so there would be a repulsive force. Now you would be saying, ma'am, you are repeating it again and again and we are just got bored. So my dear students, you don't need to get bored, because this is a very interesting topic. Why interesting? Because if I am talking about the forces that is existing in this world, in this universe around us, we must be knowing about that. And being a physics student, you should be aware of each and everything going into the surrounding. And when we are physics students, so that it becomes mandatory for us to know about the basic unit of life, the elementary unit of life, that is atom. And inside the atom, we are learning about the nucleus. And inside the nucleus, now we are learning about neutron and proton. So how they are bounded to each other inside the nucleus. If this is the nucleus, suppose if this is the nucleus, proton and neutron are just filled inside it. You will be saying, ma'am, you are drawing this diagram since 2 or 3 lectures. But yes, of course, I have to do this because we are learning about the nucleus. So I am just imagining the nucleus is somewhat like that. The radius of this nucleus, the diameter of this nucleus is approximate equals to the 10 raised to the power minus 14 meter. That means it is a very compact thing in which these are bounded. Now you can imagine yourself, if there is such a repulsive force and they are just so much tightly bound in the sphere, then isn't it that this nucleus would be unstable, because this is the repulsive force. So they are going to repel and the nucleus will then fall apart. But this is not happening. So what is the reason behind it? It becomes worthwhile for us to know about how this nucleus is stable. Well, if I talk about the nuclear stability, then comes a term mass defect. Why? Because if you are going to observe the mass of nucleons that is present inside this nucleus and the mass of complete nucleus, you would be watching that there is a difference in them. While it should be equals to each other, because just look at this side, if I am saying that nucleon is the composition of nucleus, that means nucleus is composed of neutron and proton. So, the mass of neutron plus mass of proton should be equals to what? This should be equals to the mass of nucleus. Don't note it down because this is just to make you understand what I am trying to explain you. This should be equal to this. That means mass of nucleus should be the mass of the components that is present inside it. But this was not happening. The reason is mass defect. Now here comes the term mass defect. Why was is not possible? Why was this not happening? Because as we have covered one topic, that was the mass energy equivalence. If you would have remembered, we have covered one topic of mass energy equivalence in the previous chapter, in the previous lecture. And here and there we have said that E equals to mc square, right? Now we were saying that it should be happening, but in actual it was not happening. In actual, what we had observed was this mass of nucleus was less than the mass of individual sum of these mass of proton and neutron. So what then the condition which Einstein had given us, the mass energy equivalence, has been verified. How? Because he was saying that you can be converting, you can say that mass is equivalent to energy and energy is equivalent to mass. So this is how you can just unify the law of conservation of energy and mass into law of conservation of energy. This was according to Einstein. So he had used one thing, that is E equals to mc square. And so he said that this E and this m are equivalent. So that means if there is some, okay, first of all let me introduce mass defect before you. What was mass defect? When we had observed this thing, that mass of nucleus was less than the total sum of the mass of nucleons, then that decrease in the mass was called as mass defect. So if I just write the definition of mass defect, okay. Now I think we can remove this definition if you would have just noticed. All right. First of all, I would like that it is found that what I was explaining you, I am just writing that. What was found? It was found that mass of stable nucleus is less than the total mass of constituent nucleons. That means what? That means this condition was not getting fulfilled. While it should be the ideal condition, it was not getting fulfilled. We have observed this, that mass of stable nucleus was coming less than the total mass of constituent nucleons. That means what? That means the mass is going where? Where is the mass going? The decrease in the mass of the stable nucleus was called as mass defect. So we can write it as the definition of mass defect as the difference between the sum of masses of, now I think you would be getting it what I am trying to write over here. This is just a definition, but I know you have now cleared with the concept of mass defect just by this line. This is what mass defect is. So we can just write the definition because this is a formality that we have to do. Yeah, so we have to write. So the difference between the sum of masses of nucleons constituting the nucleus and the rest mass of nucleus is called as mass defect. Now read the definition and you would be clear with that. The difference between the sum of masses of nucleons, that means this total mass of the constituent nucleons, and the rest mass of the nucleus, this stable nucleus, was different. There was a difference between these masses, and that difference was called as mass defect. Alright? So now the question is, where is that mass going? Why is the mass getting decreased? Because according to Einstein, this mass has been converted into the energy by which these nucleons are binding together. Listen me again, I am repeating myself. This mass that has been decreased, the mass defect that has been used as an energy in binding the nucleons in the nucleus. So again, the concept mass energy equivalence has been followed. That means mass is now equivalent to energy, and this is how the mass energy equivalence of the Einstein has been verified by this nuclear physics. Okay, so if the term has been said from my mouth, that is nuclear physics. So can you tell me what is the branch of physics that we are studying right now? Because physics is composed of number of branches, isn't it? And we are now studying the modern physics. And modern physics is what? In which you are going to study about the dual nature of matter and radiation. You are going to study about the structure of atom and nuclei. You will study about the quantum physics. Basically, that is the modern physics. So if anyone says you which is the chapter or what is a branch that you are studying, don't forget to tell him we are studying the modern physics, alright. So now come back to the topic now, and the topic was going on the mass defect. So basically now you are clear with the mass defect, and we denote this mass defect as delta M. It is denoted by delta M. So we can now write the mass defect as, if I am going to write it in the formula, so that would be, this is mass defect Now, what will be the mass of stable nuclei? If suppose this is the, I am having this structure, chemical structure, and I have to find the mass defect of this. So, the mass of nucleons will be what? M into ZA minus Z. This will the mass of neutrons. Sorry, I should correct it. This is not the nucleons. Okay, first of all, let me tell you, we know that this A is the mass number, and this A's mass number is what? Number of protons plus number of neutrons. So, that means A equals to Z plus N. And this X is Z is what? This Z is the number of protons. Alright. So, if you have to find the number of neutrons, that would be A minus Z. So, N would be A minus Z, and this is the number of neutrons. Now, one thing, if we have to find the mass defect in this case, how we are going to proceed? Now, look at this. We are saying that mass of nucleons, that means mass of protons plus mass of nucleons, is greater than the mass of nucleus. So, I am just going to rub this definition of mass defect, and now from here we are proceeding to this side, and we are proceeding according to this whatever statement has been written over here. We know that mass of protons will be, or you can write it as total mass of proton will be MP, that means mass of protons into number of protons, that means Z. Okay? And if I speak about the total mass of neutrons, then that would be mass of neutron Mn into total number of neutrons. Total number of neutrons is what? A minus Z. So, this is A minus Z. Alright. Now, what? We have total number of nucleons now, mass of nucleons. Now, what will be the mass of stable nuclei? Mass of stable nucleus is M into capital M. It is denoted for the mass of nucleus. Alright. So, this is now you are going to see how we are going to write the mass of a nucleus. So, this is how we denote the mass of a nucleus, because this is the structure and this is the number of neutrons in that. This is the mass of nucleus, total mass. So, now according to the mass defect, what we can say that, if I am going to now remove this, you can see here, you will be saying that ma'am is writing anywhere, she doesn't know how to write, but I am sorry my dear students, because I can just say sorry, I am not having any excuse. Okay. So, just now proceed to this side. Now, the total number of total mass of protons, neutrons and nucleus we are having. So, the mass defect now will be this mass of protons, okay, I can write it as capital M, protons into Z plus neutrons, this minus the mass of stable nucleus. So this is the formula for mass defect. Alright. After so many discussion, we have now reached to this final formula for the mass defect. Just mark it. Alright. So you just noted down this line, which is a very important thing about mass defect. Alright. Now if I just consider one thing now, the binding energy. We are just covered the topic of mass defect, and now we will be talking about the binding energy. And now from here I can write one thing, that it is the mass defect which becomes the cause of stability of nucleus. So we can write it as which appears in the form of binding energy. Now here comes the term binding energy. That means binding energy is what? Binding energy would be that energy with which the nucleons of the nucleus are fixed inside this nucleus. Or that means you can say with the energy with which they are bounded inside the nucleus. And one more thing you can say, that the energy required to extract one neutron out of the nucleus will be called as the binding energy. So now we will be going into detail of what binding energy is. But basically you should write it firstly. Just note it down, cover the concept of mass defect, and then we will be moving towards the binding energy, alright. So just note it down. Oh my God, we have done one thing that is wrong. And what is wrong? This is not such a big mistake. By mistakenly I have written small n here. But we have considered the capital N as the number of neutrons, nucleus, mass of nucleus. So just change one thing, please make a change in your notebooks, that is, it is not small n, this is a capital N, because small n here is denoting for the number of neutrons, the mass of neutrons, and capital N is being denoted for the nucleus, the mass of nucleus. So make a little change in your statement. Now what the binding energy is, alright. So okay. As I have told you that the mass defect has been converted into the binding energy. So I can write the binding energy as EB equals to delta mc square. Delta m is what? The mass defect, right? So we can now define the definition of binding energy as, alright. So first of all, if I am going to explain for it, we know that when a nucleus is composed of nucleons, and we are saying that the total mass of the nucleons is greater than the mass of stable nucleus, and which is due to the mass defect. So due to this mass defect, this energy is being equivalent to the mass defect, and that energy is called as the binding energy. Now you would be saying that, ma'am, you are getting confused, you are making us confused by saying it, by repeating it again and again. But what could I do, what can I do, because this is the same theory that would be repeating. This is the same thing that you have to understand and fix in your mind. So that is why it is being repeated, so that you can understood it in a better way, alright. So if I write the energy equivalent to mass defect Now the first line that I have written over here is completely saying itself whatever I have explained you. Equivalent to mass defect. Energy equivalent to mass defect. That means E equals to mc square. This is used in binding the nucleons inside the nucleus. And it is called as binding energy. So just write the definition of binding energy so that you would become more clear about this energy. Don't let your energy down, because this is the binding energy and this will make your energy bound to the green colored board over here, alright. So just note it down. Now we will be discussing again the binding energy, but yes, what else? There is one more thing, that is packing fraction. There is a term that you should be knowing about. So firstly just you note it down, and then I am going to rub the board and we will be starting from here. Okay, you have studied the binding energy. Have you listened any term, the binding energy per nucleon? Yes, there exists a term binding energy per nucleon which you would be aware of or unaware of, I don't know. But here we are going to discuss about binding energy per nucleon. Now since you are knowing about binding energy, so it will be easy for you to know about what is binding energy per nucleon. It is that average energy which is required to extract one nucleon out of the nucleus. It is that energy which is required to extract one nucleon out of the nucleus. So we can write over here, it is the average energy which is required to extract one nucleon from the nucleus. Okay? And it is denoted by binding energy per nucleon, or this is denoted as this, and binding energy is written as this EB. We denote this binding energy as EB, and EB is equals to delta mc square, where delta m is mass defect. In the first line, in the beginning, it is itself saying that energy equivalent to mass defect. That means the mass which was decreasing at the time of binding of the nucleus. Suppose if there were individual nucleons, that means neutrons and protons. In that case, they are having individual masses. But in case if they are just binding, if we are trying to bind it together, how can they are binding? Because at that time there is a high repulsive force, but instead of that they are binding, and they are binding at that time the mass of the nucleons is greater than the mass of the stable nucleus. That means the mass of individual nucleons was found to be greater than the mass of the stable nucleus. That means at the time of binding, the mass was decreasing, and we can say that according to Einstein, the mass which was decreasing was being converted into the binding energy, due to which these nucleons are bound towards the nucleus, bound inside the nucleus. So basically this was the whole story. How did the nucleus formed? How do the nucleus is being stable? So this was the scenario of the discussion of the stability of nucleus. Well, if I talk about the binding energy per nucleon, suppose if I have to eject or extract one particular nucleon out of the nucleus, then the energy that will be required will be called as binding energy per nucleon, simple as that. Alright. Now if I just speak about the packing fraction, what packing fraction is, I will tell you, but firstly let me tell you one more thing. There is the binding energy curve that we are going to study, but in the next session, not now. In this session we are just learning about the basic of what mass defect is and what binding energy is, and nothing else. So the binding energy curve would be discussed in the next session. Basically it is the introduction of the binding energy and mass defect. Okay, so if I just speak about the packing fraction now, if you would have noted it down, I can remove it. Oh sorry, not mass defect, this is packing fraction. Now what is packing fraction? There is a definition of packing fraction is that binding energy per nucleon is called as packing fraction. That means how tightly they are packed. How much binding energy is being exerted in between the two nucleons. That will be called as the packing fraction. And let me tell you one more thing, more the binding energy, more stable it will, the nucleus is. That means more energy will be required to extract any nucleon out of the nucleus. Understand? So basically it is defined as mass defect So packing fraction, if I denote packing fraction as PF, so then I can write it as mass defect per nucleon. So this we called as the packing fraction. Alright. So this is the basic introduction of the mass energy, binding energy and packing fraction. Packing fraction is nothing but a small thing that you should be knowing about, a term which we should be aware of what is packing fraction. Now if I just take the recap of what we have covered till now, what was that? We have started with the mass defect, but basically we have started with the mass energy equivalence, if you would have known that. Just wake up. This session is not let you sleep, this is not to make you sleep or fall down, this is make you to aware about the nucleus, to aware about the basic unit of light, basic unit of life. We all are made up of one basic unit, and that is atom, which was earlier considered. But now we can say that again there are some indivisible particles inside the atoms, and that are electrons, protons and neutrons. Alright. according to Rutherford model, the electrons rotate in the orbit around the nucleus, and the nucleus is composed of proton and neutron. And when this neutron and proton just bound with each other inside the nucleus, then we have seen that the total mass of this nucleons, nucleon is what? Neutron plus proton. Together they are called as nucleons. So when these nucleons are bound together, we found that the total mass was decreased. The total mass of the nucleus was decreased. Now, if I am not wrong, you would get confused with that ma'am, you were earlier saying that mass would increase and now you are saying mass would decrease. No, my dear student, I am just speaking the same definition in one or the other manner. You can understand by whatever we have written over the board and whatever we have covered till now. So don't get confused. Whenever the nucleons are bound inside the nucleus, whenever say suppose proton is coming, neutron is coming, they were having different individual masses. But when we try to just place them together, the neutron, neutron, proton, proton, then what happened? The total mass of this nucleons was found to be greater than the mass of the stable nucleus. While it should be equals to the stable the mass of nucleus, because nucleus is composed of nucleons. So mass of nucleus should be equals to the mass of nucleus, but it was not there. So that we called as mass defect. And so we have said that this mass defect has been converted into the energy, that is binding energy, which was used to bind the nucleons. So we can say that the energy required, the energy equivalent to mass defect, again equivalent, that means the energy mass equivalence. So it is used for binding the nucleons and is called as binding energy. This is simple as that. Then we have discussed about binding energy per nucleon. That means if we want to extract one single nucleon out of the nucleus, that would be called as binding energy per nucleon. Alright. After that we have said that this is a term, packing fraction, that we should be aware of. And packing fraction is nothing but the mass defect per nucleon. So basically, or you can say per nucleon of the nucleus, because obviously nucleon, if we are talking about the nucleon, that means what? That means we are talking about the nucleus, nothing else. So I think now the session is being completed, and as I have promised you, I will be starting with the binding energy curve. So let me just tell you, in the previous session I have promised you that I will be starting with the mass defect and the binding energy. As I have given you a little bit hint about the binding energy in the first lecture, in the previous lecture, and so I have started this lecture with the mass defect and binding energy. So I have fulfilled my promise to you, and now I am again making a promise that I will be starting the next session with the nuclear stability curve, or you can say the binding energy curve. So we will be just discussing over that. Till then, you just take care. We will be meeting again with the same chapter, with the same energy, with the same topic, but the different subtopic. So till then, you just take care. We will be meeting again. Bye bye.